Thrust generation in a jet engine is a direct application of Newton's third law, achieved by accelerating a mass of air rearward. The fundamental relationship is defined by the momentum equation. Force equals the mass flow rate multiplied by the change in velocity. Gas turbine engines utilize the open Brayton cycle to continuously achieve this high-speed acceleration. The cycle begins as air enters the inlet and is subsequently compressed. This high-pressure air then receives thermal energy in the combustor. Following combustion, the hot gas expands through the turbine, extracting necessary work. Finally, the remaining energy is converted into propulsive thrust as the gas accelerates through the exhaust nozzle. The core function of the engine is to significantly increase the kinetic energy of the working fluid. Since the Brayton cycle is a continuous flow process, all components operate simultaneously on a steady stream of air. For propulsion, the cycle requires a net positive work output, meaning the mechanical work generated by the turbine must exceed the work consumed by the compressor. This surplus energy is then dedicated entirely to generating propulsive thrust. The ideal Brayton cycle models the gas turbine using 4 distinct reversible thermodynamic processes. Process 1 to 2 represents isentropic compression, where the pressure and temperature of the air increase without any change in entropy. Process 2 to 3 is defined as isobaric heat addition, simulating the combustion chamber. During this stage, thermal energy is added at a constant pressure, establishing the maximum cycle temperature designated as T3. Process 3 to 4 is the isentropic expansion phase through the turbine, where mechanical work is extracted to drive the compressor. The final stage, process 4 to 1, is isobaric heat rejection, where the exhaust gas releases heat to the ambient atmosphere. Crucially, the thermal efficiency of the ideal cycle is determined exclusively by the pressure ratio, P2 divided by P1, and the specific heat ratio of the working fluid. Efficiency increases monotonically as the overall pressure ratio is raised. The axial compressor's primary function is to significantly increase the pressure ratio of the incoming air, demanding the largest mechanical work input of the entire cycle. Modern jet engines utilize multi-stage axial compressors, ensuring the air flows parallel to the axis of rotation. Each compression stage is composed of a rotating rotor blade row immediately followed by a stationary stator vane row. Rotor blades dynamically accelerate the air, converting existing pressure energy into kinetic energy. Subsequently, the stationary stator vanes decelerate the high-speed flow, converting that kinetic energy back into pressure energy through a diffusion process. The overall compression process must closely approximate isentropic behavior to maximize thermodynamic efficiency. Achieving high overall pressure ratios necessitates the use of variable geometry stators, particularly in the initial stages. These adjustable vanes modify the angle of attack, which is essential for preventing aerodynamic stall during low engine speeds or high-altitude operation. The combustor executes the isobaric heat addition, process 2 to 3, which establishes the critical maximum temperature limit, T3, of the cycle. Fuel is precisely injected and mixed with only a small fraction of the compressed air within the primary zone to ensure stable, stoichiometric combustion. The vast majority of the compressed air is utilized for dilution and cooling purposes. This dilution is mandatory to ensure the resulting gas temperature remains strictly below the metallurgical limits of the downstream turbine blades. Combustion must occur at a nearly constant pressure to preserve the high thermodynamic efficiency inherent to the Brayton cycle. The substantial heat release dramatically increases the specific volume of the gas, preparing it for maximum expansion work in the turbine section. Advanced liner cooling techniques such as film cooling are employed to protect the combustor walls from the extreme internal temperatures. The turbine extracts essential mechanical work from the high-energy, high-temperature gas stream to successfully power the compressor and all engine accessories. This expansion process, modeled ideally as isentropic, begins with the stationary nozzle guide vanes, or NGVs. The NGVs accelerate the gas flow, converting thermal energy into kinetic energy. The high-velocity gas then impacts the subsequent rotor blades, where the kinetic energy is converted into useful rotational shaft work. The turbine must generate sufficient work to precisely satisfy the compressor's demand, a relationship quantified by the back-work ratio. Turbine blades operate under the most extreme thermal and mechanical stresses within the engine. This necessitates the use of advanced materials, specifically nickel-based superalloys, combined with sophisticated cooling methods. These methods include internal convection cooling and external film cooling, which are vital for maintaining structural integrity and preventing creep failure. The exhaust nozzle is responsible for converting the remaining pressure and thermal energy of the gas stream into kinetic energy, thereby generating the final propulsive thrust. The nozzle accelerates the gas to its maximum possible exit velocity. For aircraft operating exclusively in subsonic flight regimes, a simple convergent nozzle is utilized, where the flow area decreases continuously. However, for supersonic flight, a convergent-divergent or CD nozzle configuration is mandatory. In a CD nozzle, the flow accelerates precisely to Mach 1 at the throat and then continues to accelerate supersonically within the divergent section. Net thrust is calculated using the momentum equation, which accounts for the difference between the exit momentum and the inlet momentum. An additional pressure area term must be included in the calculation if the exit pressure is not perfectly equal to the atmospheric pressure. Real gas turbine cycles inevitably deviate from the ideal Brayton cycle due to inherent irreversibilities, primarily caused by aerodynamic friction and unavoidable heat transfer losses. Compression and expansion processes are not perfectly isentropic, resulting in entropy generation and a measurable reduction in net work output. These losses are quantified using component entropic efficiencies. Furthermore, pressure losses occur throughout the system, specifically in the inlet, the combustor, and the exhaust system, which collectively reduce the effective pressure ratio for expansion work. The gas turbine operates with a high back-work ratio, typically ranging from 40% to 60%. This means that even minor inefficiencies within the compressor significantly degrades the overall engine performance. Thermal efficiency is maximized by simultaneously increasing the overall pressure ratio and the turbine inlet temperature, T3. Conversely, propulsive efficiency is optimized by minimizing the velocity difference between the exit velocity and the flight velocity of the aircraft.